Okay, good morning, everybody. I'm very glad to be here today with you, and I will be just, explaining about what I'm doing in the group of Professor Hannes Pichler in Innsbruck. And yeah, thank you for the invitation. And also, if you have questions, you can just raise your hand. And in case I don't notice it for some reason, you can also shout. During the talk is fine, no problem. So that's exactly like what I'm going to talk about. What we're trying to do is to minimize entanglement. Hello. In tensor-network quantum trajectories that solve the dynamics of the open quantum many-body systems. I'll just begin then with the following observation. Quantum entanglement is rather a dialectical notion because on one side, of course, it is an essential resource for quantum computation, and it's important to have it. But from another side, it's a great obstacle for any classical simulation of quantum many-body systems. And imagine that we have such a system starting in some pure state, and then we represent this pure state with a standard tensor network approach called MPDO, which is abbreviation for matrix product density operator. This tensor network ansatz allows you to solve the dynamics of open quantum systems, which is usually the case in today's world, like when we have quantum devices, but they're still noisy. And what you want to do is, of course, to propagate the state in time using some sequential Newtonian to prepare the state, for example, or to do something else. And like when you reach the description of your system at time t, what usually happens to tensor networks is that they blow up in a sense that their bond dimension is becoming so unbelievably large that there is no way you can, handle it or process this or do anything with it. And yeah, there are different names for it, like bond dimension blowing up or volume law entanglement behavior, or also there is a notion of entanglement barrier, which we will explicitly see towards the end of this talk. So yeah, this is a problem. But as I already said, experimental quantum many-body systems are open, they're noisy. And this is actually something that, of course, bugs people who want to implement quantum computation, because there's a lot of problems with errors occurring, and current models of quantum error correction are not really feasible. But still, some experiments are already implemented. For example, this is an experiment from Harvard, from Misha Lukin's group with neutral atoms, two-dimensional atom arrays, or this is Rainer Platz's group in Innsbruck. They're doing some very nice ion experiments with radio frequency traps. Or last but not least, also superconducting technology allows us to have also superconducting qubits. All of those approaches are baptized as noisy intermediate scale quantum devices, right? And that's every word is important. They're rather small, and also they are prone to noise. And yeah, exactly, like if we want to be realistic about where we are at the moment, we have to deal and implement in our classical simulation of those devices the presence of noise as well as other problems, but the noise is a focus of this talk. And like the question that one would ask, can we simulate quantum open many-body systems faithfully on a classical computer? And when I say faithfully, I mean correctly and efficiently. So that is the question. And yeah, so the goal of my work is to be able to solve the dynamics of open quantum many-body systems using tensor networks as a way to describe the states. And what we try to do is we try to make the simulation of such system sufficient by exploiting the entanglement properties in the presence of noise. As a basic system, we consider the following system of size L, which has a bipartition somewhere, AB, and it has interaction within the system, nearest neighbor interaction in our case, and it also interacts with the environment in one way, meaning that it is a Markovian environment and there is no feedback. And like the basic piece of the many-body system, a body can be a spin 1/2 or spin 1 or any other, depending on the task, right? So this is the outline of my talk. I will first briefly, or maybe not, introduce you to pure state decompositions and also the way you can represent pure states as tensor networks. Then I will look at quantum channels, and then I will switch to practical domain where I will consider continuous dynamics as a quantum channel. And after that, I'll introduce quantum trajectories, the standard approach to quantum trajectories, as well as something that we developed, adaptive. And after that, I will actually explicitly show you the methods that we developed and provide you some examples and conclusions, of course. So we start with the introduction. So pure state decompositions is a very basic thing, but I will just introduce you the notation so you will have an intuition of what happens next. So imagine that you have a many-body system in some mixed states rho, and this mixed state rho can of course be written as a statistical mixture of various pure state projectors. Psi alpha is a pure state, and it kind of contributes to the density matrix with some probability with P alpha, right? And we also can write it in not normalized form. So yeah, of course, the amount of pure states that you have in your decomposition must be larger than the rank of the density matrix. This is kind of a strict bound. Yeah, and as I said, we have probabilities, pure states here, and unnormalized pure states here with the tilde on top. It will be accompanying us throughout the rest of the talk. And of course, you can imagine your state being inside of a kind of a sphere on the shell of which leave the pure states, namely the pure state projectors that are not normalized with tildes. And basically, you are like representing your mixed state by basing your state with legs on the outer shell of your sphere. We can name the bunch of the states that represent your density matrix an ensemble psi large tilde. And this ensemble, for example, can be written as a vector. And this ensemble is not unique because you can also, with the same success, represent your density matrix using a completely different set of pure states from a different ensemble phi large tilde. The amount of pure states in your vector should also be larger than the rank of density matrix. And you will have something of this sort, the same sphere, the same mixed state in the middle, but the legs are spanning to the different set of states. And yeah, these two ensembles are actually related to each other, so you can essentially perform a rotation between one and another in order to get from ensemble psi large tilde to ensemble phi large tilde, right? So it's very simple. Yeah, of course, the thing is that, as I already expressed many times, emphasized many times, you have to have the dimensions of your ensembles larger than the density matrix rank in order to represent it correctly. Yeah, so the basic take home of this slide is that we have various ensembles, for example, psi large tilde and phi large tilde, and they are like kind of equivalent because they still represent the same state in the mixed space domain. Yeah, of course, ensembles are equivalent in terms of the density matrix, but they are not equivalent in terms of different nonlinear measures and nonlinear functionals of the density matrix, one of which is, for example, the average entanglement. So E bar of an ensemble psi large tilde is essentially a weighted sum of pure state contributions to the entanglement. And here, E of pure state psi alpha is a von Neumann, for example, entanglement entropy. In principle, it can be anything else, but we are going to stick to one entanglement measure, which is like kind of the most obvious one. And E bar, this kind of functional, can be also minimized over various ensembles that can represent our state. And when we do this minimization, what we obtain is a very important notion in mixed state entanglement measures, entanglement of formation. So essentially, what you do is you transform your ensemble to obtain a new one, and you look for all of possible transformations, and you hope that in the end you will reach a minimal value of E bar of the ensemble. And yeah, it turns out that computing the entanglement of formation is a hard task, especially for a generalized mixed state, but finding the transformation that makes E bar a little bit smaller is useful. And the question is why? Well, here comes slide with tensor-network. So basically imagine that we have our state rho, which is represented by psi pure state, and the pure state that comes into the ensemble, that represents rho, can be represented as a matrix product state, the simplest tensor network there is. And here I drew it in the so-called gamma lambda form, where gamma corresponds to essentially a body in many-body system, while lambda kind of where it contains the information about the singular values or Schmidt values and tells us about the structure of the entanglement between parties. For example, here it will be between first and the rest. Here it will be between the two and the rest, and so, right? And yeah, we have a physical dimension D, which is staying constant throughout any kind of simulation, usually. But there is also a bond dimension, which is the dimension of this matrix of singular values. And this bond dimension can grow, and this can become a problem because whenever you do a normalization of such an object, you will depend on the size of this matrix as chi to the power of 3, which is enormous whenever you have a growth, linear growth, for example, in case of volume law entanglement of the bond dimension, then essentially you are soon kind of dying and not able to do anything. Oh, sorry. And yeah, as I said, bond dimension grows with, oh, I didn't say that. Yeah, I say it now. Yeah, bond dimension is actually intimately related with the amount of entanglement. So whenever an entanglement in bipartition AB starts to grow, whenever there's like quantum correlations appearing between two parties, you will have your bond dimension grow, and thus amount of singular values which are important and which cannot be cut off becomes larger and larger. And this is the relation between the von Neumann entropy of the pure state at particular bipartition and the singular values which are contained in the diagonal matrix lambda. And yeah, therefore, we come back to what I just said before, lowering E bar in your decomposition of pure states of your mixed state is actually kind of useful because in the end, it minimizes the overall computational cost of your processing. And yeah.
So in the definition of E bar, you minimize over all von Neumann entropies, but do you do that along all cuts in the MPS or all bipartitions?
In principle, you can do along different bipartitions, but for a practical reason, usually in MPS, you can stick to, for example, middle cut, because this is the maximum possible entanglement that can be, and you just minimize that, and usually it kind of results in automatically reducing the unneeded correlations everywhere else. But actually, it's a good question because indeed, you can do some studies where you minimize at different places and see how the pure states that decompose your system are going to be slightly different, right?
So are your examples naturally 1D systems?
Here, yes, yeah. But in principle, you can also do things with multi-dimensional systems. There is like for example, you can do something with PEPs, right? But it's a bit more complicated and doesn't serve really the purpose of methodology that I'm trying to develop, right? You're gonna show some simple, intuitively understandable, and also like simply codable examples. Right?
Yeah, no, what I was asking is you could have had another system that's say 2D, but then you snake it.
Yeah.
But then it starts to make it, then just looking at the bipartitions according to the 1D structure maybe is not the only. But if you're doing it to a 1D system, then that's.
Yeah, I mean, in principle, the snake thing and looking at different bipartitions there can also be an objective, but there probably I'll show you later that basically the closer is the channel, like the noise channel to the bipartition, the better. So basically you can do something like if you have a snake, then when you come to the optimization of the nearest channel to the first bipartition, you optimize this bipartition, and when you go around and optimize the next channel, which is close to the second bipartition, you optimize that one. So it's like, you can do many actually things, there's a lot of freedom. Right, okay, we go on. Yeah, I started talking about something that I didn't yet explain, so maybe we should first go through that. So second thing I wanted to mention is notion of like quantum channels. So imagine that you have a system starting in a pure state, which is sent through some quantum channel, math called E, and the resulting state is a mixed state rho. In principle, you can write the action of quantum channel in the form of a Krauss representation, where you have Krauss operators that are a completely positive map. And again, you can already feel the analogy. The amount of Krauss operators that represent your channel must be larger or equal than the rank of the output density matrix rho. And yeah, you can also maybe look at it as this kind of sphere again, where you have resulting state rho after the channel, and it bases itself upon different pure state projectors produced by the Krauss representation. Okay. And yeah, we can write Krauss representation as mathcal K, which is a vector containing all the operators that represent our quantum channel. And this Krauss representation K, mathcal K, is also not unique, because you can write the same density matrix, the same action of the same quantum channel, is a different set of Krauss operators which form mathcal R. And again, as before, these two things are isometrically related in the sense that you can transform the initial Krauss representation mathcal K into mathcal R and so on. And yeah, again, the outcome of this slide is that representations are mathcal R and mathcal K are equivalent because they essentially give you the same dynamical map, like the same quantum channel. Right. Now we move on to the second step, which is, okay, we consider a single quantum channel, but in principle, we can also do the same trick with a sequence of quantum channels, right? So if you start with a pure state and then send it through the first quantum channel, which is in turn sent through the second and so on, until we reach the resulting mixed state rho n. And this can be written as here. So we start with initial state and we have first, second, third, nth quantum channel, and we get the output state. Now, of course, every quantum channel in this sequence can be also associated with a certain Krauss representation mathcal Ki, which has a set of operators like that. And we can write the final output state rho n in this kind of pure state decomposition form, where we apply in different combinations cross representations from various steps. And we can also write it as a sum over unnormalized pure state projectors psi tilde. And there is an analogy between, as we already saw, between the Krauss representations applied in sequence and these kind of pure states that live on the shell of the sphere, where mixed state is inside the sphere. And kind of next thing to say is, of course, you can, instead of considering the discrete sequential quantum channel, you can consider a kind of quantum channel that is going to represent us a dynamical map of a continuous dynamics. So in this very specific case, what we want to consider is so-called Markovian quantum channel, which enjoys the property of semi-group structure that you can essentially, instead of just applying a single big quantum channel, which is written explicitly here, you can apply many of those in a sequence and maybe like reduce the amount of terms that you have to deal with and like use trajectorization and stuff, right? And yeah, I mean, quantum channel of Markovian type, of course, has this very kind of famous Invladian superoperator in its core, where you have the part which corresponds to the coherent evolution, this is the Hamiltonian H, and then you have a part, second term, which corresponds to the coherence process by the fact that the system interacts with the environment, where you have the coherence rate gamma and jump operator C. And yeah, as I mentioned, yeah, we have this property that we can apply many small little channels, which are in this case mathcal E dt. And this is essentially the same channel, but with the step dt. And this channel is really simple in terms of its Krauss representation. It has a Krauss representation of only two Krauss operators, one corresponding to the non-Hermitian evolution with the Hamiltonian, and another corresponds to a so-called quantum jump event in the system. And this like important outcome of this slide is that we can essentially reduce the dynamics of our open quantum systems to applying quantum channels with ranks of Krauss representations being just two. And we can use this smallness of rank of our quantum channels to our advantage, as we will see further. So yeah, we are continuing on with continuous dynamics, and we want to write the final state rho of t, also in this kind of pure state decomposition form, whereas you remember the tildes are essentially the result of application of sequences of combinations of Krauss operators on the initial pure state. And we can also write it as a weighted sum, essentially a statistical mixture of a pure state projectors with some probabilities p. And again, we can also put it on some kind of sphere for simplicity of understanding. And like now we come to the point where we can actually introduce the method of quantum trajectories, and where we see that essentially what quantum trajectory method does is it samples from this distribution sequentially, like time step by time step, and the number of trajectories that is sufficient will recover us the density matrix at empty. So yeah, quantum trajectories. Imagine that we again start with the pure state initially and send it through the first continuous small dt quantum channel mathcal E dt. And we consider, for example, the case where the first channel is represented by a representation mathcal K, which contains two operators, as you remember. So basically, you can write the action of quantum channel explicitly as basically the first and second term, where P0 is the probability of the state ending up in psi 0, and P1 is the probability of psi 1. And what we do, or we can also visualize it, of course. So essentially, when we apply the mathematical K representation, we send our state to two possibilities, namely psi 0 and psi 1. Those two states together in a weighted sum like this recover us the density matrix at step 1. And now what we do is, instead of just taking the density matrix and continuing with that, we want to stay in the pure state domain, and therefore we just sample stochastically one of the two states from this nice distribution. And we, for example, end up in one of the two. And what we do next is we apply the second channel to the state which we obtained. So depending on what was obtained, for example, we obtained at the first step psi 0 randomly, and then we start applying quantum channel mathematical E2 dt to the second, to obtain the second like kind of two branches of possibilities. And we basically again stochastically sample this state and then going on. And by this we construct a quantum trajectory. So a quantum trajectory in our case here is the blue line. And this is a single instance of quantum trajectory. And in order to represent the density matrix at later step, you have to explore this tree of possibilities, explore the most probable situations, so the most probable probability, the most probable trajectories, right? And then you will be approximately recovering the state at the later time. Now, this was the Krauss representation mathematical K, and this actually corresponds to a very well-known in quantum optics method called quantum jump method, or number unraveling. It's related to the fact that you measure the environment degrees of freedom in a number basis, in a Vovk basis, essentially. So this is one thing. The next thing is when you consider a different Krauss representation, and imagine that we again start with the first channel, and now we use a different Krauss representation, mathematical R, which is a transformed version of mathematical K, and we will receive different pure states with different probabilities. And this transform, in the case of 2x2 transformation, is very simple. It's a SU2 kind of transformation, where you have two parameters, theta and phi. And again, we can consider the possibility tree again. When we use the representation mathematical R, we obtain two states, phi 0 and phi 1, which again give us the same density matrix as before. And what we do with quantum trajectory construction, we stochastically sample from the two to remain in the pure state domain. And again, as before, by complete analogy, we construct this tree, and we essentially every time choose one of the possibilities and explore like the state space by trajectories in the pure state domain. And yeah, again, as before, at the second step, we apply our second quantum channel to the state that we obtained at the previous step. And in this case, this representation mathematical R, when we set theta to be pi over 4, is corresponding to another very well-known quantum optical method to simulate quantum dynamics, which is called quantum diffusion, quantum state diffusion method, or also homodyne unraveling, because the measurement is now happening in homodyne basis. Now, the kind of important slide is, okay, we considered number, we considered homodyne, but what happens if we choose the representation of the next step based on the state that we obtained from the previous step? So this is what it is about. So imagine that we again send our state through the first quantum channel, and for example, for the first step, we choose a Krauss representation corresponding to a number basis. We again have these two possibilities from before, from representation mathematical K, and we stochastically choose between the two as before. But now, second step will be a little bit more difficult, or rather non-trivial, it will depend very much on what outcome we had on the previous step. So imagine that we have psi 0, so alpha 1 is equal to 0. Then the channel mathcal E2 will be represented by representation mathcal R. Otherwise, when we choose psi 1, it will be represented by mathcal K. And this constitutes the so-called adaptive representation of a quantum channel, which we call mathcal A, with an index alpha 1, where alpha 1 tells us like that there is explicit dependence of the transformation T alpha 1 on the previous state. And yeah, in this case, we will obtain this kind of branches. And for example, we end up for the second step choosing this new state, which is a little bit unusual because it is now the state, the second index of which depends on the previous index. And this index depends in a way how we represent the quantum channel. So this is how it's written. And here again, the cross operators in the representation, they explicitly depend on what happened before somehow, right? And now, like the main kind of goal that we reached is that we can use this idea of adaptive representations of quantum channel in a sequence of continuous dynamics to minimize the average entanglement throughout the actual unraveling. So during the simulation, in a greedy way, like step by step, we can choose an adaptive representation in such a way that we obtain a lesser E-bar at every time. Yeah.
Can you go back to the other picture? So when you, so every time there are these two possibilities, when you go either one way or the other, there is some probability of going there. And like, isn't there also another thing you would try to optimize is to try to have one of these probabilities much bigger than the other? Because then you would, like if these probabilities are always equal, it means that you will be sort of like each of these paths will have equal probability. Right. And so you will have to sample many times to kind of explore the space. But if you were lucky and these probabilities were always, one was much bigger than the other, you would sort of mostly take the same path and all the weight would be kind of concentrated in a few samples. So, I mean, maybe there's also some trade-off in terms of like what you were saying, you were trying to minimize entanglement. So maybe it means the computation will be using less memory because the bond dimension is smaller, but maybe you need to run it more times because if these probabilities are very similar, then you need sort of many samples.
That's actually a very good question and a good intuition behind it. Indeed, whenever there is like one dominating situation happening in your trajectory, then you will most of the time choose this trajectory and then maybe add a few which have these additional like situations with very small probability, and this lies in a kind of core of this method that I showed the first. This is so-called quantum jump method, and the jump word here tells you that essentially the system almost every time evolves according to the Krauss operator K0, which is just some kind of non-Hermitian evolution, but then suddenly the jump occurs and you end up being in this state. And this is the configuration essentially where like the probabilities are mostly unbalanced, like that the probability of 0 is like almost 1 and the other one is like almost vanishing. It is true that the noise properties of the trajectories that you construct with quantum jump method, the amount of variance that you have in your statistical averaging is smaller, but in the same time, on the other hand, usually as we will see, quantum jump will require a larger bond dimension. So there is exactly this trade-off, and indeed it's also a good question to consider the convergence properties of your trajectories and whether you should simulate just 2 times more for one unraveling than for the other. But we didn't implement it yet, but we have this idea in mind. It's actually very important, right? Okay, I'll move on with the adaptive representation that we just saw. And now what we want to do is actually implement this adaptive representation with a single goal that we want to minimize E bar. So adaptive entanglement optimization is consists in the following problem. So we call it here individual continuous entanglement optimization. Essentially, at every time step, what we want to do is to reach the minimum of E bar of a transformed ensemble where transformation that we minimize over goes over isometries. And we have an ensemble that is obtained by a default Krauss map, K0, K1. And we have an isometric transformation. And according to Kara-Theodore theorem, it's actually quite useful to have your Krauss representations with a small rank, because you will have to explore the optimum, the optimal isometries of limited size. And actually K times K squared is the maximal possible needed isometry to actually reach, safely reach the absolute minimum of the E bar at this time step. And one can consider the time derivative of the quantity that we are minimizing and obtain a time derivative of the average entanglement, which we call E bar dot ECO after the name. But in principle, one can think about also exchanging the limit and the minimization operation. And what will happen if we do that, we will obtain a slightly different value, which also has a name and which we introduced actually in the paper here. Oh, sorry, it should be 16. Entanglement optimum quantum trajectory. Okay, those names are just names, and I will just use abbreviations. So EOQT and ECO throughout the rest of the talk, referring to this essentially exchange of limits here. And it turns out that if you think about it, actually, this EOQT gives you an upper bound of the minimal possible time derivative of entanglement, of average entanglement. But first, let's consider this EOQT method that we already kind of proposed recently, or not recently. Essentially, what happens with this EOQT method is that because of the operation of time derivative, the optimization becomes trivial because it revolves around choosing between two possibilities, namely number, as we already discussed this one, and R, homodyne with theta pi over 4. There is nothing in between, and it's like you just calculate one, another, compare, check, select. And yeah, exactly, like at every time dt, what we do is we calculate what happens if we evolve with number measurement or quantum jump approach, what happens if we evolve the system using homodyne representation. And we see that in contrast to the linear functional, like density matrix itself, non-linear functional like E bar will be dramatically different. And we have advantage to choose the configuration that gives us on average, this solid line here, on average, it gives us a lower average entanglement. But because we have to stochastically choose between the two trajectories, which are shown in dashed lines, we'll end up in one of the two, and we will end up in a pure state at time t plus dt is an entanglement E of t plus dt. And we can continue with the second step again, just calculating number, calculating homodyne and selecting. And again, and it's super simple and efficient. This method is also very easy to perform using matrix product state contractions, so it's very computationally beneficial. But the drawback of this method is, of course, as we discussed, it doesn't always reach the optimum. And we, as a first example, consider bell pair dephasing under the excited state projector. So, and what we plot here is the difference between E bar, the average entanglement, with the minimum. As you remember, entanglement information is the minimal value that can be reached by E bar. So if we plot the difference between the two, what we have is the so-called excess entanglement, which would basically mean the amount of additional computational effort that you have to apply in order to simulate with this method. Because on the bottom lies the ideal case where all the computational effort that you apply is useful and actually represents quantum correlations, while this additional computational effort will represent you unneeded classical correlations. And we see that in different cases of measurements, we observe that, for example, number measurement is performing very bad in the beginning, while then dropping lower than homodyne, while homodyne performs better in the beginning and then kind of loses to number, while the method that we implemented, which chooses between the two at every time, as we see here, it first selects always the homodyne, and indeed, like, it's very similar to the dynamics of homodyne, but later it kind of starts to select more and more number measurement, and therefore it deviates from the homodyne curve. So yeah, the method which involves minimizing the time derivative of E bar already finds a very good configuration with a smaller entanglement. Now what we would like to consider is a many-body setting. So imagine we have a many-body system of size L starting in a product state of excited states, and we apply to it a quantum channel with Lindbladian, which has both coherent and incoherent part this time. The coherent part is a random Brownian circuit. This is a Hamiltonian, which contains of different combinations of Pauli, because we have a Stillman half chain, weighted by random Gaussian variables. So this is an example of a fast scrambling Hamiltonian, which in the case of coherent evolution leads to a volume law entanglement growth. But we still have an incoherent process. And now the question is how we use this incoherent process to our advantage. And here on the plot, and yeah, we have a dephasing process with sigma z over 2. And here on the plot, we show the evolution of the entanglement E bar averaged over different realizations of both quantum trajectories and the random Hamiltonian. And we plot this quantity versus time for different unravelings. And we see that on the bottom, we have homodyne with phase 0. On top in gray, we have homodyne with phase pi over 2. The lines in between correspond to the in-between phases. Also on top, we have a number measurement. And on the bottom, we have our entanglement optimal quantum trajectory protocol. And you see that essentially number measurement as well as homodyne with pi over 2 are giving us this typical linear growth of entanglement in time, while the entanglement optimal trajectory and homodyne with phase 0 will remain in the area low phase. And one can also look at the steady state and entanglement cuts in different bipartitions at the steady state here. And one will see that again, the number measurement is giving us this famous triangular shape of entanglement distribution, which refers to volume law phase, while these two curves, like green one and the red one, will give us an area law with a constant value of entanglement throughout chain. And we can also calculate how does this middle cut entanglement at the steady state scale with the system size to convince ourselves again that both homodyne with phase 0 and our optimal method give us something which saturates with the system size at larger system sizes, which is a sign of an area law, while the other methods, for example, number, are giving us a volume law entanglement entropy, which actually implies that the bond dimension will blow up. Right. So the take home is that entanglement optimal quantum trajectory method finds an area law phase, which is good. Yeah.
Sorry. So when you select the which way you're going to go based on you're trying to minimize entanglement, but it could be that you just end up in a trajectory that contributes very little to the, like the probability of actually taking that trajectory, if you would use the actual probabilities, would be really small. And so, like, but does it does it tell you something about the system? Because, you know, it's like, you know, you could have your stake could be, yeah, there could be just many different contributions, and maybe the significant ones actually have lots of entanglement. You just kind of throw them away, and you say, okay, there are some, you know, contributions that have very little entanglement, and you kind of zoom in on those. Maybe they just have little weight actually.
Whatever what you're saying, that would be a bad way to perform the optimization, because when you focus and zoom in on improbable trajectories that have a lesser entanglement, it means that you kind of alternate the probability distribution, and you actually have dynamics with a different density matrix.
Yes.
So we are not doing that. We actually sample the trajectories according to the probabilities that appear in front in the pure state decomposition. And it doesn't matter what kind of representation we choose, the probability distributions stay the same. And therefore, when we actually sample according to these real probability distributions, we end up in the same with the same density matrix, right? But the states that represent our density matrix with true probability distributions that will give us this density matrix, they can have different entanglement properties. They can have higher or lower. Yeah.
Well, I think I probably misunderstood that. So, like, you're not deterministically choosing which path to take.
No, I don't choose the path. Yeah, this phrase is something that is important to clarify. I'm not choosing where to go. I'm choosing how to go.
Okay.
Is there any intuition for why such low, such pure states with the area entanglement scaling exist in the mixture? Because if you would just normally time evolve, for example, I'd expect this not to happen. Say with a closed system.
Yeah,
So
I mean, with a closed system, for example, in this particular case, you will have a volume law for sure, because there is no noise that destroys the entanglement build up in the system, right?
Yeah.
But whenever you have noise, now it depends how you measure it, right? Or how you, okay, in what we just discussed in this language, how you represent the quantum channels corresponding to the noise process. Depending on how you represent it, you will either end up in pure state decomposition, which is extremely entangled and actually doesn't serve the purpose of simulation, or lower entangled and still gives us the same dynamical properties.
Yeah, I see, but my question is a bit, is it specific to this Hamiltonian that such low, such area law states exist? Or can you do this more generally?
Yeah, so it is specific not to the Hamiltonian, but rather to the noise and the strength of noise. For example, below here, you probably don't see it well, but the variance of the random Gaussian coefficient in front of the Hamiltonian terms divided by the gamma is 0.4. So like gamma has a critical value. When gamma is larger than a certain threshold value, it will there will be a possibility to find an area law phase, because actually what happens to the real physical device is that the entanglement that builds up with the Hamiltonian is destroyed. But if gamma is lower, if this ratio is higher, then there is actually no way, and those two curves will actually also lift towards the higher values. And at some point they will coincide with the volume law. When the gamma is essentially 0 and this is infinity, everything will be like the blue line. Right, so it's more specific to the noise and to the strength of the decoherence process.
Right, so if I understood correctly, you were choosing between two decompositions every time. Would it make sense to choose this isometry like uniform return every time to kind of scramble up the decomposition every time?
That's exactly what I'm going to talk about now. Okay, it's good that I build my talk in such a way that you have this suggestion. All right, so the next thing that we want to consider now is this new method of optimization, where we actually, instead of considering the time derivative, we consider the E bar. And here I just shortly mentioned that we will explore only 2x2 isometries because for a small time step, it's already sufficient to reach the minimum. But I mean, in principle, you can explore larger isometries. It will just take more time and more parameters to optimize over. But okay, look, so we have this new representation corresponding to optimization of this object. Now, we will have also homodynamic number as before, but apart from that, we'll have other possibilities, and actually a continuum of possibilities that is corresponding to transformations with different parameters here. And we will have to explore them all in order to see that sometimes there are decompositions that lie above the standard quantum trajectory methods, which give you a lower average entanglement entropy and thus nicer pure state decompositions. And we can select one of those and we can do it again. We can again explore the span of all possible pure state decompositions that correspond to different ensembles. And we can always select the configuration which gives us a smaller entanglement entropy on average. And yeah, again, as I said, ECAO, this method of minimizing E bar is very different from minimizing E bar dot, where it turns out that only two possibilities remain and everything else is basically equivalent to them. And yeah, so the kind of good side of the ECAO is that it actually guaranteedly reaches the minimum for E bar at the time step dt, but it does not efficiently, it cannot be efficiently implemented with matrix product states and contractions of them, and therefore it's kind of a bit of a rather a good observation than a practical way to do it. But if we consider again the Bell state example phi plus with the coherence, the same plot that we had before with excess entanglement, whenever we implement ECAO with this setting, we will actually always reach the entanglement of formation, which is an amazing thing because now whatever computational effort we apply to simulate the decoherence of these two qubits, it will be exactly enough to do it and no more. We will not have to spend more computational effort to simulate those two things. And if you look at the histograms of trajectory distributions of simulations with different methods, on the background you have the entanglement optimal quantum trajectory, the previous one, that is kind of diffusely distributed and explores the whole space of possible configurations with different entanglement entropies, while ECAO is a sort of deterministic way to represent quantum channels at every step because it doesn't have any diffusion and it kind of automatically finds a configuration which always has the same value, which is the entanglement of formation. So yeah, it kind of is interesting, but unfortunately, it's only with these very small examples with very symmetric noise processes where it actually occurs naturally. Of course, in like further examples, it will not be the case and we will see it. Here, I consider also two atoms with a single decoherence process. And here I focus on the dependence of the optimization landscape on the amount, the value of the time step, right? Time step comes into the definition of our cross representation, it is just there. And depending on the value of dt, the Krauss operators in Krauss representation mathcal k will be slightly different. And the expectation is that the optimal value of the transformation parameter theta will be different for different time steps. And indeed, for this very specific demonstrative case of slightly entangled pair of qubits, where slightly entangled is such that one coefficient is 0.98, so it's really like slightly entangled. And here, when you apply a single quantum channel referring to the coherence of the first qubit, you will observe this dependence of the time derivative on the isometry parameter and on the time step. And you see that when we approach the time step towards smaller values, we see that the theta tends to be more and more close to 0, which corresponds to our cross representation with number measurement. And when we actually take the limit, what we see is that the optimal measurement becomes out of a sudden homodyne, because this kind of dip disappears. And at the point when theta is 0, we have a kind of divergence towards this 0 value, which means that there is no change in entanglement entropy when we apply the channel. And out of sudden, we switch to the optimal measurement being homodyne, while when we actually consider the finiteness of the time step in our numerical simulation, we will have to choose something over here. Yeah, so again, entanglement of optimal quantum trajectory does not depend on time. It kind of removes the time dependence from the equation, and it considers time derivatives, and because of that, it's a bit of a different approach, and the optimization landscape is rather binary, while ECO does depend on the time step, and we see that the optimization explicitly depends on the value of the time step. And here I just briefly show how, in the case of two qubits, again going through a decoherence of first qubit, how the time derivatives of the new and old method relate to each other. And we see that at almost every time for different initial states, we observe the ECO method gives lower values of time derivative, which means a better optimization. And here I plot for a single decoherence channel, I plot ECO versus entanglement of formation, and we see a full equivalence. Means that ECO method gives us something which recovers fully, in this very specific case, entanglement of formation. However, what happens when we scale a system size up? For example, imagine that we have 10 qubits with a middle cut bipartition, and we have a single decoherence channel at 5th qubit, so just in front of the bipartition. And what we have here is, again, ECO versus AOQT. And we see again that in this very specific case also, the entanglement optimization is better with the ECO method. And as I already mentioned, it's important to have the decoherence channel close to the bipartition over which you optimize. For example, if I would put my decoherence here, it wouldn't be as much of dramatic difference. So whenever you have a many-body system and you would like to optimize like channel by channel, sometimes it makes sense to optimize over closest bipartition. That's kind of the message. Now, the next thing is we have now two atoms again, but now we have two channels. And it's important to see that whenever you optimize channel by channel, one after another, you actually have a deviation from entanglement of formation, right? So now ECO is worse than entanglement of formation after two subsequent steps of our algorithm, which demonstrates that it's not an ideal algorithm, it's a greedy algorithm that actually, whenever you have multi-channel configuration and multiple time steps, it already becomes kind of a little bit not perfect. Well, entanglement of formation and finding entanglement of formation in such configurations as per se an NP hard problem, and therefore, I mean, it's good that our algorithm, which is super simple, doesn't do it, right? I mean, otherwise it would be very surprising and probably not right. So it's good. So we see that our algorithm is not perfect, but it works still very well, as we see here. Again, consider a big chain with random Brownian circuit as before, and consider different unraveling strategies, and consider the entanglement exponent evolving in time, the distribution of the trajectories of this value. And we see that, look at the scale here, the number measurement with sigma z over 2 as a jump operator basically blows up. It means that here the state is no longer computationally representable, it's just a very large matrix in your tensor network. While homodyne, AOQT, and ECO show moderate values of the entanglement exponent, which is related to one dimension. And we see that ECO if you look hard, you see that TCO is giving us even better distribution in terms of entanglement exponent, which means that bond dimensions that appear in our trajectories with this method are always a little bit smaller, which is also a good thing to observe. Now, like this is the second to last slide, what we have here is a discrete circuit case with which we study the difference between quantum trajectories and matrix product density operator, which appeared in the beginning of this presentation, right? So what we do here is imagine that we have a state initially in Bell pair configuration. So imagine many, many Bell pairs in infinite chain, to which we apply swap operators plus these little tiny dots, which refer to a decoherent quantum channel, right? So with probability P, there will be application of sigma z. So without these little squares, the swap circuit will basically spread the Bell pairs around the chain, and it will result in volume law growth of the entanglement versus the number of steps. While when we have the decoherence process, we can, depending on the representation of this quantum channel, we can either have no effect on the entanglement on average, or we can have a great effect using quantum trajectories. The thing is that whenever you represent your states initially and propagate using matrix product density operator, it actually doesn't help us that we have a decoherence channel, because it will end up growing rapidly like this. So entanglement entropy will grow as a volume law, and we will end up being in a bad situation. While in the case of quantum trajectories with number, we will have the same, but with homodyne or ECO, we will, depending on the decoherence strength, we will actually obtain better and better configurations. And you see that the dashed line is the entanglement of formation, the absolute fundamental minimum, while the line with dots is the homodyne, which is a simple, non-optimized, just kind of good guess, okay? And the line with the crosses is the optimized version of the so adaptive Krauss representation, and we see how close this line gets to the entanglement formation. Unfortunately, it doesn't coincide with it because we still are in a configuration of infinite, infinite chain that we have to optimize step by step, and it's not as good as, for example, a single decoherent channel. Right, and then basically the last slide of my talk is the same thing, but a continuous version, which is nothing but Ising modulo with fields, antiphasing sigma z over 2. And we basically what we see here, what we plot here in these three plots is values of correlations of the first with the second and seventh, sigma z, different, so evolution of these values for different bond dimensions and the exact solution. So exact solution is this black dotted line, probably you see it, while the bond dimensions refer to different maximal bond dimensions that we allow in our tensor networks. And in case of MPDO, we have to take the squares of the trajectories because the Hilbert space dimension is squared. But what you see is that 256 is an exact solution. It indeed coincides with the actual exact diagonalization. While when we reduce twofold the bond dimension, we already see a deviation starting at time gamma t equals to 1. And this also happens already, I think, in case of a number of quantum trajectories, it happens a bit later with gamma t over 2. While in the case of homodyne, it doesn't happen for 8 and almost doesn't happen for 4. So it happens, of course, the deviation happens with bond dimension 2. And this is a good illustration, which is accompanied by this plot here, which is the dynamics of entanglement entropy measures versus time. While entanglement entropy with trajectories, we talked about it a lot. Entanglement of MPDO, what we plot here is the base for operational entanglement, which is a good measure to see how many correlations you have in your tensor network and how one dimension grows. And we see that in the MPTO case with this Hamiltonian, this noise process, we have this famous entanglement barrier that I talked about in the beginning. And this thing we cannot overcome if we want to simulate the full dynamics of the system at all times. There are methods that can give you steady states avoiding this entanglement barrier, but it's not always like working like very well, especially when you want to see the dynamical situation at every time step. Well, when we simulate with trajectories using quantum jump approach, we are staying in area law, but end up being slightly larger than the MPTO entanglement. Well, when we simulate in a smart way, choosing, in this case, it's just a coincidence that homodyne is the optimal one. A homodyne stays always in an area law, lower at all times than the MPTO complexity, which basically is the last final message I want to deliver. So my conclusions are we developed tensor network approach to simulate open quantum systems, and we use the fact that the system is open to reduce the computational cost, which is given by the average entanglement entropy. And we, in this kind of ways to reduce the computational cost, we came up with two different ways, one of which is ensemble optimal quantum trajectories, giving an efficient way to reduce the entanglement, which gives an upper bound to the minimal cost, while ECO is an honest way that sometimes even reaches configurations with the minimal entanglement. And however, because it's honest, it's a little bit less efficient. So with this, I thank you for your attention.